Well, good morning. I do trust that you guys had a good first week of class. We are in our second week now, and this week is when we're going to start getting into the meat and potatoes of aviation weather. This week, we're going to be talking about the atmosphere and things that you need to know and be made aware of so that you are confident in your flying abilities and knowing how to look at weather and be able to tell and make competent go, no-go decisions. So, without further ado, let's jump right into it, okay? So, let's see if we can get this working. All right, now that we've had our technical glitch, let's jump right into this. All right, so this is section 1, the atmosphere and causes of weather. All right. So the atmosphere. What is the atmosphere? So the atmosphere is a protective blanket that is essential to life on Earth. It is an envelope of gases that surrounds our planet. So imagine wrapping a beach ball in a piece of paper. That would represent our atmosphere, okay? 99% of the atmosphere exists within 30 kilometers of the surface. So our atmosphere is composed of 3 main ingredients. 78% is nitrogen, 21% is oxygen, and there's 1% other gases. They're also known as trace gases. So let's talk about water vapor. So water vapor is a percentage of water vapor in the atmosphere, and it can vary greatly depending on your location. As much as 4% of the atmosphere will be water vapor over tropical areas and over the deserts and high altitudes. Now, what you need to understand is that water vapor is an important gas for weather production, even though it exists in very small amounts. Now, this can exist in the form of liquid, regular water, or in a solid state as ice. Now, water vapor contributes to the formation of fog, clouds, precipitation, and icing, which are all very important aspects to you as a pilot. Water vapor also absorbs radiant heat from the earth, which reduces cooling. Okay. Ozone. Now, ozone, or O3, is toxic. It's highly reactive pollutant which is produced in the lower atmosphere by the sun, by the action of the sun oxidizing with nitrogen by electrical charges such as lightning. The greatest concentrations of O3 are located between 50,000 and 100,000 feet above the Earth's surface. The upper ozone layer is beneficial to us because ozone absorbs harmful ultraviolet radiation from the sun. Now, I'm sure you've heard, ozone's bad, ozone's bad, ozone's bad. No, ozone is actually very good. The hole in the ozone layer, what that allows to happen is it allows more ultraviolet rays to hit the surface, and that is what's bad, okay? So just remember that ozone is good for us. The hole in the ozone layer is what allows more ultraviolet rays to hit the surface. Therefore, it can cause more skin cancers, things of that nature, and it can cause us to be warmer, all right? Particulates or aerosols. Now, these can be liquid or solid particles that are small enough to remain suspended in the air. Some might be large enough for you to see, but most are not, okay? Most obvious are water droplets and ice crystals associated with fog and clouds. Now, these are what you'll learn in later chapters are called condensation nuclei. These are things for water droplets to attach themselves to and form an actual droplet, Okay. Other sources include volcanoes, fires, dust storms, industrial processes, automobile and aircraft engines. Whenever we burn a carbon-based fuel, it puts particulates into the air that you may or may not be able to see, okay? Now, these are important to aid in the absorption of radiation, and it provides surfaces for condensation nuclei to develop a water droplet around, and these will reduce your visibility as a pilot. So let's look at our atmospheric properties. Now, there's three things that take place in the atmosphere that you need to be aware of, all right? And these things are temperature, density, and pressure. Now, when you combine these things, this forms what is known as the gas law. The gas law states that if you take pressure and you put that over density and temperature, it gives you a constant. Now, temperature. Temperature is a measure of hotness or coldness. It can also be defined as a measure of the motions of molecules. Now, this is very important because throughout aviation you will learn about kinetic energy and potential energy. Kinetic energy is energy that exists by virtue of motion. So let's say that we take a parcel of air. We have a parcel of air and we have molecules all throughout this parcel of air. All right? So once these molecules of air start bouncing off of one another, it creates heat. Now, the more these things get bounced around and start moving around one another, the higher the temperature. This is all known as kinetic energy. Okay? So this gives you a little visualization of what kinetic energy actually is. So kinetic energy is energy that exists by virtue of motion. All right? You need to remember that. Kinetic energy is energy that exists by virtue of motion. Please remember that. Say it one more time. Kinetic energy is energy that exists by virtue of motion. Okay? Now, temperature is defined as the average of kinetic energy of the many molecules that make up a substance. The greater the average kinetic energy, the greater the temperature. A temperature of absolute zero is the point where all molecular motion ceases. I'll repeat that because you need to understand it. The temperature of absolute zero is the point where all molecular motion ceases. So, absolute zero is on the Kelvin scale, and at absolute zero, molecules do not move. They are suspended, they are frozen. Absolute zero, all molecular motion ceases. Remember that. Let's talk about density. Now, density is the mass of the molecules in a given area. If the total mass of the molecules decreases, then density decreases. This is very important when we're going to go into density, altitudes, things of that nature. So just remember, if the total mass of the molecules decreases, the density decreases. Pressure. Pressure is the force exerted by moving molecules over a given area. So pressure equals the force over a given area. P equals F over A. So pressure is the force over a given area. Things like pounds per square inch. Okay? So a typical value of atmosphere pressure at sea level is 14.7 pounds per square inch. This equates into 1,013.2 hectopascals. That's the scientific term for it. Most people will call that millibars. Or 29.92 inches of mercury. Okay? This is very important to you as a pilot, and you need to remember these numbers. 14.7 pounds per square inch at sea level equates to 1,013.2 hectopascals or millibars, or 29.92 inches of mercury. Now let's look at the gas law. So we've already determined that P over pressure over density and temperature gives you a constant. Now the ratio of pressure to the product of density and temperature is always the same. In aviation practices, we will measure pressure and temperature to calculate density. Okay? So reducing pressure relates to cooling, reducing mass, and increasing volume. So you need to be aware of this. All right, let's look at our atmospheric structure. So the dimensions of our atmosphere. So the circumference of our planet at the equator, so all the way around the equator, is 21,600 nautical miles. Okay? Now the radius is 3,438. So if we were to draw a line, as the slide shows, from pole to pole, and measure from the pole out to the edge, it would be 3,438 nautical miles. Now the distance from the North Pole to the South Pole, the distance from the North Pole or the South Pole to the equator is 5,400 nautical miles. So let's look at our atmospheric layers, okay? Now, you have everything, we reference everything off of sea level, okay? So from sea level up to flight level 180, or 18,000 feet, 50% of the mass of our atmosphere is in this level. So 50% of the mass of our atmosphere is from 18,000 feet down to sea level. Now from 18,000 feet up to 53,000 feet, 90% of our atmosphere, the mass of our atmosphere, is in this level. So 90% of our atmosphere is between sea level and 53,000 feet. Now, if you take from 53,000 feet down to sea level, you're going to find 99.9% of the mass of our atmosphere is in this range. And that's approximately 27 nautical miles high. Okay? So let's look at our temperature layers. Now, layers are very important. All right, so there are 4 main layers that we're going to study in this course. And they are the troposphere, the stratosphere, the mesosphere, and the ionosphere. Okay? So let's talk about the troposphere. Now the troposphere, I'm going to blow this up a little bit so you can see it better. So the troposphere is where most of Earth's weather takes place. And that is generally from sea level up to, in our latitude, about 36,000 feet. Okay? Then it transitions into the stratosphere. Now, the layer of transition between the stratosphere and the troposphere is known as the tropopause. Then we will continue on up through the atmosphere to approximately 160,000 feet. And then we start transitioning into the mesosphere. Now the mesosphere, that transition point, is known as the stratopause. Now as we travel on up, I said the ionosphere, but that's even higher, but it's actually the thermosphere. So we're going to go from 160,000 feet up to 280,000 feet, and that's when we start transitioning into the thermosphere. Now that transition layer between the mesosphere and the thermosphere is known as the mesopause. Okay, so our four main layers of atmosphere that we're going to focus on are the troposphere, the stratosphere, the mesosphere, and the thermosphere. Now the ionosphere is on higher than that, and we're not going to worry about that. But these are our four main layers that we are going to concern ourselves with. Okay? So let's look at the troposphere and the tropopause. Now, these are very important. The troposphere is the lowest layer of our atmosphere. All right? So average temperature in the troposphere decreases with altitude. So the higher you go up in the troposphere, the colder the temperature gets. This is the layer of the atmosphere where a majority of the clouds and weather on Earth takes place. Okay? The top of the troposphere is about 36,000 feet in our latitude here, and it is known, once you reach that top, around 36,000 feet, that is known as the tropopause. Now this is where you start to transition from the troposphere into the stratosphere. It's known as the tropopause. Okay? The troposphere is normally associated with a wide variety of weather phenomena such as jet streams, clear air turbulence, and thunderstorms. Altitude of the tropopause varies with season and with the location on the globe. So you need to remember that. It's not all the way around the globe. It's not always at 36,000 feet. It depends on what latitude you're at. Okay? It might be lower, it might be higher. So you need to remember that. So now let's talk about the stratosphere and the stratopause. Now, in the troposphere, the higher you go, the colder it gets. But when we break into the stratosphere, it reverses. And the higher you get, the warmer it gets. So that's the main difference between the troposphere and the stratosphere, is that the higher you go in altitude in the stratosphere, the warmer it gets. So you need to remember this. Now in the stratosphere, air is confined to move more or less horizontally, not vertically. Okay? Now, stability of the atmosphere and instability of the tropopause, or the troposphere rather, are more directly related to the variation of temperature with altitude in these layers. The stratopause occurs at an altitude somewhere around 160,000 feet above sea level. All right. Now, temperature reaches a maximum value at the tropopause height. So remember that once you go through the tropopause and you keep going up in altitude, temperature gets warmer, with a maximum temperature being reached at the stratopause height. Okay? So now let's talk about the mesosphere and the mesopause. Now the mesosphere is a layer where temperature again decreases with altitude. Now this extends to a height of roughly 260,000 feet above sea level, and that's when you'll reach the mesopause. Now the coldest temperature in the mesosphere will be located at the mesopause. Okay? So now let's talk about the thermosphere. Now this is the height layer where temperature again generally increases with altitude. Objects in space at such heights have temperatures that are more closely related to a gain in temperature through radiation. Okay, at these higher elevation, you're getting more ultraviolet sunlight and things of that nature, so therefore the temperatures will be higher. All right. So let's pause here just for a second, and I want to kind of go over this again. Okay. So if we have our atmosphere, here, okay? So down here we have sea level. And let's say up here we have 36,000 feet. Okay? We know that this is the tropopause. Right? So this is the tropopause. We have sea level up to 36,000 feet. This is the tropopause. So let's just draw our line across here. So we know that temperature, as we go up through the troposphere and we hit the tropopause, we know that temperature decreases. So temperature decreases as we go up through the troposphere and we hit the tropopause. But then, as we climb through the tropopause, we go up to the mesopause. If we was to draw a line across there, then we know temperature again increases as we go up through the mesosphere. But once we break through the mesopause and we go up to the thermopause, temperature again decreases. So as you can see, as we go up through the atmosphere, the different layers of the atmosphere, temperature decreases, increases, decreases, and then increases again. The higher we get in the atmosphere, temperature at the highest levels will be hotter because we have broken through the point where the ozone layer is, which we're about to discuss. The ozone layer absorbs a lot of the ultraviolet light. Therefore, temperatures at the lower levels of the atmosphere are normally cooler because of that ozone layer. The higher you are, the closer to space you are, the more radiation that you will absorb, and therefore you will be at a higher temperature. Okay? Now, let's go back and let's talk about this ozone layer. Okay? So the ozone layer is very important to life on Earth. It's found in the lower atmosphere. Now, the maximum concentration of O3 or ozone is located somewhere around 80,000 feet MSL. Okay, you need to know that. So there is an increase in temperature with altitude in the stratosphere. We know this. Okay, and now this is due to absorption of solar radiation by the ozone layer. Pretty simple. The higher we go up, the warmer it is in the stratosphere there, because the ozone layer, which is located in the stratosphere, is absorbing a lot of the solar radiation. Therefore, our temperatures are going to be higher. Now, here's that ionosphere that I was talking to you about earlier, okay? So I'm going to blow this up so you can see it just a little bit better. Now, the ionosphere is a deep layer of charged particles, ions and electrons, that extends from the lower mesosphere upward through the thermosphere, okay? So the ionosphere is actually in the thermosphere and extends out past it. Charged particles are a result of solar radiation displacing electrons from atoms and molecules, okay? AM radio waves were reflected and or absorbed by different sublayers in the ionosphere. radio communication may be influenced during periods of greater solar activity. Okay, so whenever there is a solar eruption, a solar flare, that's how you know. That's when you notice like cell phones will be interrupted or disturbed. Radio waves will be disturbed. That's why, because during the ionosphere, that's where a lot of this stuff happens. That's where a lot of the radio waves and cell phone waves, and that's where they're contained, is within that ionosphere. When there's a solar flare or solar eruption and we're bombarded with a lot of radiation, it gets disturbed in the ionosphere. So that's why we have those disturbances, okay? So let's talk about pressure versus altitude just for a little bit. So pressure decreases rapidly above sea level and very gradual at higher elevation or higher altitudes. This demonstrates the compressibility of the atmosphere and the lack of a well-defined upper surface. The concentration of oxygen is a mixture, or in the mixture of atmospheric gases, is proportional to the total atmospheric pressure. Now, this says that therefore oxygen levels decrease with the height in the same manner as total pressure. Now, this is a little misnomer. This is something that gets people confused a little bit, but I want to kind of sort of set it straight for you just for a minute, okay? The amount of oxygen as we go up through the atmosphere does not change. If we look back at the beginning of the presentation, we know that our atmosphere is composed of 78% nitrogen, 21% oxygen, and 1% other gases or trace gases. So that amount of oxygen is the same from the surface up. The difference, however, is the pressure. As we rise throughout the atmosphere, the pressure's less. Well, we have to have partial pressure for our bodies to infuse that oxygen into our blood, for our red blood cells to be able to pick it up and carry it throughout the different organs and different systems of our body. The pressure is less, therefore we can't use the oxygen that is available at those altitudes without that pressure, okay? So there are several important physiological effects related to flight at high altitudes because of the pressure being different and our bodies not being able to absorb the oxygen that is there because the pressure is less. And we're going to talk about some of them, okay? So, supplemental breathing oxygen is recommended above 10,000 feet MSL during the day and 5,000 feet MSL at night. Now there's a key word there, recommended. It's not a requirement, it's recommended, all right? In an unpressurized environment such as an aircraft, above approximately 40,000 feet, supplemental oxygen must be supplied under, keyword, pressure. Has to be supplied under pressure. Why? Our bodies can't absorb it. So if it's not under pressure, we're not going to be able to use it. Okay? Now this is a cool fact. And I want you to do a little research on this and see for yourself. So the government had an aircraft called the Blackbird, the SR-71 Blackbird, and it could fly at altitude 60, 70,000 feet. Okay? Those pilots had to wear the same pressure suit that astronauts wore. Why? Because at approximately 63,000 feet, the pressure exerted by the gases escaping your body, your blood will literally boil. Think of that. At 60,000 feet and above, if you do not have pressure on your body, the gases escaping your body will boil. Therefore, your blood will boil at those altitudes if you do not have a pressure suit on. So pilots above 50,000 feet, they wear a pressure suit. And this is why. Not only does it aid your body in absorbing the oxygen needed for you to sustain life, but if you don't, your blood's going to boil. Pretty interesting thing. All right, so let's talk about standard atmosphere. So as a pilot, different countries, different regions, we don't have different things because travel, air travel especially, is worldwide. So we had to come up with a standard for everyone to use. That's what we've done. Now, International Standard Atmosphere, ISA, you need to remember this, ISA, International Standard Atmosphere, is an idealized, I want to really push this point home, it's idealized atmosphere with specific vertical distributions of pressure, temperature, and density prescribed by international agreement. ISA is theoretical. You're not going to go and say at 22,000 feet, this is what the temperature and pressure is. It's not going to happen because it's different everywhere. So this ISA is an idealized, this is a perfect environment that countries have agreed to around the world to be the standard, okay? Now, although ISA is a useful tool in aviation, it's mandatory, okay? There are large variations from standard conditions in the real atmosphere. That's what I was talking about just then. So we had to come up, or the different countries of the world, they had to agree to something where they would be the same all over the place. And that's what ISA is. Now, the standard atmosphere is most representative of average mid-latitude conditions. Therefore, the troposphere is actually colder and the tropopause is actually lower than international standard atmosphere over the poles and respectively warmer and higher over the equator. Our world is not a perfect circle, it's kind of like egg-shaped. So you're going to have those differences. Now, in the international standard atmosphere, ISA sea level, you need to remember these. I promise you, you will see these things again, and you will need to know these as a pilot, okay? So ISA at sea level, the pressure is 29.92 inches of mercury, or 1,013.2 hectopascals, or millibars. The idealized temperature is 15 degrees Celsius, or 59 degrees Fahrenheit, okay? In the lower troposphere, pressure decreases about 1 inch of mercury or approximately 0.34 hectopascals for each 1,000 feet gained in altitude. In the ISA troposphere, the temperature decreases 2 degrees Celsius or 3.5 degrees Fahrenheit for each 1,000 feet of altitude gained. So for every 1,000 feet of altitude you go up, in the ISA, you lose 2 degrees Celsius, okay? You need to remember these numbers and become very familiar with them. So let's talk about energy transfer. Now, everything that deals with weather on Earth is done by energy transfer or heat exchange. And you will see that in just a little bit, okay? So solar energy enters the atmosphere and undergoes a series of energy conversions which produces wind, clouds, and precipitation. Heat energy must, keyword must, be transferred as well as redistributed within the atmosphere. Now this is done by three main ways: radiation, conduction, and convection or advection. Radiation. Now, radiation transfers energy by electromagnetic waves. Okay? Conduction transfers energy through molecular motion. Now, convection, advection, they transfer energy through movement of mass. Okay? Now, convection, commonly referred to as, I'm going to blow this up because it's hard for me to see and I want you to be able to see it as well. Convection is commonly reserved to mean vertical movements, advection, horizontal movements. All right? So let's talk about radiation. So we know we get radiation from our sun. Now, conduction and convection and advection require mass for energy transfer. Therefore, the transfer of energy from the sun across space must be accompanied primarily by radiation. Solar radiation received at the Earth's surface varies by what latitude you're in and what season you're in. Okay? Let's see, here we go. So the intensity of solar radiation received depends on the following, okay? The time of day, the time of year, and what latitude you're in. So I'm going to clear this off and I'm going to draw on the board just for a second. So as I stated earlier, Earth is pretty much shaped like an egg. And we know that we have a pole here and a pole here and we have an equator, right? But Earth is not just sitting in one round spot. Earth actually sits on an axis of 23.5, not percent, I'll get it right in a minute. It's 23.5 degrees. So Earth actually sits in space at an angle to the sun of 23.5 degrees. Now this is very important. Why, Shannon, is this important? Why do we need to know that Earth sits at 23.5 degrees? Very simple. That 23.5 degrees, that's what gives you your seasons. That's what, spring, summer, winter, fall, all because of that 23.5 degree tilt and how the Earth hits the sun with that tilt. Okay? So, equinoxes. Let's talk about that. I was just talking about changes of season because of that 23.5 degree tilt. So let's talk about equinoxes. Equinoxes are the first day of spring and fall. Okay? The sun's rays are perpendicular to the Earth's surface at the equator during the equinoxes. Now, the solstices are the first day of summer and winter. Let's see. Normally, the sun reaches its highest point at lowest latitudes, respectively somewhere around 66.5 degrees north and south, okay, during the summer solstice. So that means that summer and winter, those are our longest days of the year, okay? So you got the sun hitting it perfectly, even, so as the Earth moves, days are longer, all right? So let's talk about the solar elevation angle. The solar elevation angle is the angle of the sun above the horizon. All right? If the angle is small, solar energy is spread out over a broad area. And it minimalizes heating. But if the angle is large, solar energy is more concentrated in a smaller area, makes it hotter. So let's take it for in the wintertime, okay? So in the wintertime, the angle is small, therefore we have a cooler, colder temperature. During the summer, the angle is big, it's large, therefore we have hotter weather during the summer, okay? Now, let's talk about radiation. The radiation process happens by electromagnetic energy, radiates from any object that has a temperature above absolute zero. Okay, because what happens at absolute zero? Absolute zero is the point where all molecular motion ceases. So if there's no molecular motion, you cannot have radiation. Okay, so it has to be a temperature above absolute zero. As energy enters the Earth's atmosphere, 19% is absorbed by the atmospheric gases and clouds. Approximately 30% of incoming solar radiation is lost due to reflection, scattering by clouds and other particulates, and reflection from the Earth's surface. So this is a little diagram. I'll blow it up so you can see it a little bit better. So this just shows you that, and on arrow 1 there, 19% of solar radiation is absorbed by the atmosphere. 51% is absorbed by the Earth. 6% is scattered from the atmosphere. 20% scattered and reflected back by clouds. And 4% is reflected by the surface. So, terrestrial radiation. So during the day, the loss of terrestrial radiation, and that's mostly infrared heat, is offset by the receipt of solar radiation, temperature, and you'll have a temperature increase. Now during the night, the surface cools very rapidly due to no solar radiation hitting it. Now, during this time at night, the Earth continues to radiate energy that it stored during the day. This is a phenomenon called diurnal variation. Now, diurnal variation is very critical in the day to night changes in wind, ceilings, and visibility. And as we go through this course, you'll learn what ceilings and visibility and all that is. Visibility is self-explanatory, but you will learn what ceilings are, okay? Now, this is also an important control of surface temperature, terrestrial radiation, and heat, and this is the heat capacity. Now, heat capacity is the amount of energy that is necessary to raise a temperature of a substance to a certain point. Okay? So if you got a pot of water and you want that pot of water to boil, the heat capacity is the point where the water boils. So the heat capacity is what you have to raise the temperature of the water to get it to boil. Okay? So water has 4 times the heat capacity of typical dry soil. All right? Water vapor is important in the absorption of radiation. Large amount of water vapor prevents radiation from leaving the atmosphere. All right, so I want you to think about the southwest versus the southeast. All right, now the southwest, there's not a whole lot of water there, it's desert. Now the southeast, Florida, there's a whole bunch of water, right? And during the desert at night, you're not going to see clouds. Florida at night, you're going to see clouds because it can radiate that back up into the atmosphere, condense, and make clouds, okay? So the capture of terrestrial radiation by certain atmospheric gases is called the greenhouse effect, and we all know what that is. So I just wanted to throw that in there to make you aware of it. Doesn't have anything really to do with you in aviation, okay? So let's talk about conduction. Conduction is a transfer of heat by molecular action through a substance from one to another, but they have to be in contact. Okay? So that same pot of water that was on the stove earlier that we're bringing to a boil, we put a metal spoon in there. Now, the heat capacity of the water is what we have to raise the temperature to get the water to boil. Conduction is the process of the spoon, the metal spoon, becoming hot because it has conducted heat from the water into the metal of the spoon. Now, it always has to go from a warmer surface to a colder surface. So from warm water to the cold spoon, the spoon gets hot, you have conduction. Okay? Now, air is a poor conductor. Most significant energy transfer by conduction in the atmosphere occurs at the Earth's surface. Okay? So at night, the cold ground conducts heat away from the air immediately, close to the ground, touching the ground, right? So during the day, solar radiation heats the ground, which, you know, that's your conduction right there. By the air, the solar radiation comes through the air, it goes down to the ground, comes back up and heats the air close to the ground. It's touching it. There's your conduction. Let's talk about advection and convection. Now, both contribute to the unequal distribution of heat. Without it, polar regions would be extremely cold and the equator would be extremely hot. Advection includes the north-south movement of large, warm, and cold air masses. Convection includes a large-scale ascent and descent of air masses and smaller-scale developmental thunderstorms. All right? So let's talk about this. I'm going to blow this up, and I want you guys to listen very closely. Okay, let me blow this up. There we go. So in aviation, you will be dealing with Celsius, the Celsius scale. Okay, now you need to understand how to convert Fahrenheit to Celsius, Celsius to Fahrenheit. All right. Now on your quiz that you will have to take at the end of this lecture, I'm not going to have you work any conversion problems, okay? But what you will have to do, excuse me, you will have to know the formula for the conversions, all right? So the conversion from Celsius to Fahrenheit is your degrees Celsius times 9/5. Now, if you will look over to the side, you will see that I got on here 9/5 equals 1.8. So you can substitute 1.8 for that 9/5, all right? Plus 32 degrees will give you your degrees Fahrenheit. So in the example provided, 15 degrees Celsius times 9/5 equals 27 degrees. 27 degrees plus 32 degrees equals 59 degrees Fahrenheit. Now the conversion from Fahrenheit to Celsius is your degrees Fahrenheit minus 32 degrees Fahrenheit times 5/9 or 0.56. And that gives you your degrees Celsius. So as you can see here, 59 degrees Fahrenheit minus 32 degrees Fahrenheit equals 27 degrees Fahrenheit times 0.56 gives you 15 degrees Celsius. So like I said, you will not have to work any problems, but you will need to know these equations for the quiz coming up and any section test or midterms or finals or whatever. You will need to be familiar with these formulas. All right, so temperature measurements. Surface air versus upper air temperatures can give you an indication of how stable that parcel of atmosphere is. All right, so IAT, indicated air temperature, is temperature of the air as is measured by the temperature probe on the outside of the aircraft. Now, every aircraft does not have a probe. The planes you're flying here, it's just up on the air vent. You can look right there, there's the thermometer, it tells you, right? Outside air temperature, OAT, is also called true air temperature. Now, it is determined by correcting the indicated air temperature for compression and friction. Because we know if you take your hands and rub them together, what happens? Your hands get hot, right? That's friction. So air going across your aircraft does the same thing. So outside air temperature or true air temperature is corrected for compression and friction heating. Now, a sounding is nothing more than the National Weather Service taking a big weather balloon and sending it up through the atmosphere, and then the atmosphere recording the temperatures throughout the different locations and layers throughout the atmosphere. That's all a sounding is, okay? All right, so large variations between winter and summer, and also between the poles and the equator. That's just common sense. We know that it's a lot colder at the poles than it is at the equator, and there's quite a bit of temperature spread in between the two, okay? Variation also occurs between large land masses and bodies of water. That's pretty self-explanatory. All right, so let's talk about a temperature gradient. So a temperature gradient is nothing more than the change in your temperature divided by the distance at which it changes. So if you've got a 20-degree temperature change between Memphis and Little Rock, and it's 100 miles, you'll take 20 divided by 100. Your temperature gradient is 0.2. Very simple. All right, so areas where isotherms, lines of equal temperature, not to be confused with isobars that you will learn about later on. Isotherms are lines of equal temperature, are close together. If they're close together on a chart, that means the temperature gradient is relatively large, and there's a large temperature change over a very small distance, okay? So impact of the Sun-Earth geometry on temperature distribution is large. I mean, depending on where you're located in the world, what angle you're at, what time of year, time of day, depends on the temperature change and the distribution of the sun's radiation over a large area, okay? Advection, convection, and absorption of radiation by the ozone becomes more important in the determination of the temperature distribution, okay? Below the tropopause level, cold poles, and you'll have cold poles and warm equator. That's what we have down here on the ground. So the equator is warm, North and South Pole are cold, okay? Temperature differences are important in explaining the characteristics of the jet stream, a strong band of winds. Now you will learn about the jet stream, and after you leave here and you start flying, cargo, airlines, whatever, you will need to be aware of the jet stream, okay? So let's talk about some moisture characteristics. Greatest concentrations of water vapor are found over the tropics, over the oceans. Imagine that, right? There's a lot of water there. You're going to have a lot of water vapor, okay? Many of the flight hazards encountered in aviation are due to the presence of water vapor, water, and ice in the atmosphere, and you will learn about that throughout your aviation career, all right? H2O, or water, can be present in 3 states in the normal range of atmospheric temperatures and pressures. Water vapor, which is colorless, odorless, tasteless gas in which molecules are free to move wherever they want to move, all right? It could be in the liquid state where the molecules are restricted to that droplet, or it can be in the solid or ice state. Molecules are even more rigid. I mean, it's cold, it's frozen. They're still moving in there, but it's not very much at all, okay? Now, the change of state refers to transition from one form of water to another. Now, the transition of water molecules to a higher state can go by melting, evaporation, or sublimation. Now, melting is strict, we all know what that is. It's ice to water. Evaporation is water to water vapor. Now, sublimation is something you've probably never heard of, and that is ice going directly to a vapor. Think of dry ice. You take dry ice out, it's a block of ice, but when it melts, there's no water. It goes directly to vapor. That is sublimation. Okay. Now the transition of water molecules to a lower energy state comes by condensation, freezing, or deposition. All right. Condensation is water vapor to water. Think of the dew in the mornings. Freezing, we know what that is, water directly to ice. But deposition, something you've probably never heard of, is water vapor directly to ice without going through the liquid state. So it goes from water vapor straight to ice. That's deposition. Now you will need to know these, okay? So make sure you understand the different changes in state, okay? Now let's talk about latent heat. Now this is kind of an interesting topic, okay? So latent heat is the amount of energy that is absorbed or released, hidden, latent means hidden, when water changes from one state to another, okay? So let's think about a cloud. So I have here my little bubbly cumulonimbus cloud. As the heat rises and goes up, more clouds are going to form. Well, when more clouds form, latent heat is pushed out. That latent heat rises, and more clouds will form. Okay? So latent heat is a byproduct of water going from one state to the next. Very simple. Okay? Now, sensible heat is just heat that can be measured. All right? Now, the release of latent heat when condensation occurs is a major source for many meteorological circulations. Instability and vertical development of thunderstorms, which I was just talking to you there about. When heat is taken away from the tropics through evaporation, it becomes a primary source for hurricanes. Now, I'm sure most of us have watched the news or Weather Channel or something like that when their hurricane seasons are on. We've seen hurricanes. And you hear them talk about it's moving over much warmer water. The warmer water, evaporation, feeds the hurricane. Okay, that's what this is talking about. Let's talk about saturation. Now, saturation, I'm going to blow this up. This is a little smaller again. But saturation occurs when the same amount of molecules are leaving a water surface that the same amount's returning and that's leaving, okay? The significance of saturation that it provides a limit for the amount of water vapor in the atmosphere that the atmosphere can hold at a given temperature. Now, this becomes very important when we start talking about dew and dew point, okay, which I think those slides are coming up. So relative humidity. The formation of clouds or fog can be determined by how close the atmosphere is to saturation. In simple terms, the amount of moisture in the air compared to what it can hold. Very simple. The amount of water vapor needed to saturate the air is largely depends on air temperature, okay? So we're going to talk about this a little bit in a little further detail in just a second. Here you go, a dew point temperature. So what is a dew point? Now you need to remember these. The dew point is the temperature to which the air must be cooled to become saturated. Now, this is always going to be less than the air temperature, except at 100% saturation point. And that's when the temperature and the dew point are equal. All right? So the temperature dew point spread between, that is the temperature between the air and the dew point. Now, when the temperature spread is small, like less than 5 degrees, relative humidity is high. When you have a large temperature dew point spread, relative humidity is low. This will become very important later on when we start talking about fog, okay? The amount of water vapor needed to saturate the air largely depends on air temperature. So let me blow this back up, another small one. So dew. Dew is a condensation product that forms when the ground or other objects lose energy through nighttime radiation. When the temperature reaches its dew point, dew condenses on the colder surface. Frost is a deposition product which forms when the same conditions favorable for dew, except that the dew point is below 32 degrees Fahrenheit or 0 degrees Celsius. Okay? So when you see frost, that means that if it was above 32 degrees, it would more than likely be dew. But because it's 32 degrees or below, it's frost. All right? So when you take all of this information and you condense it, you come to one commonality. Okay? This is very important. You need to remember these right here. Okay? The sun is the source of all weather on earth, regardless. The sun is the source of all weather on earth. Now, and the process by which weather is created is heat exchange, or the uneven heating of the Earth's atmosphere. So if you see a question on a quiz or an exam that says, what is the source of all the weather on Earth? It's the sun. And if you see a question on a quiz or an exam that says, well, by what process does Earth's weather occur? It's heat exchange or the uneven heating of the Earth's surface. All right? So this is the end of Unit 1. Okay, I hope you guys have learned some things. All right? Now you'll have to take a 20-question quiz. Now to unlock this quiz, you're going to need the password SUN, S-U-N, all in capital letters. Okay? Good luck on the quiz. And don't forget that you have a discussion post and everything due by 11:59 this Saturday night. I bid you a good week, and I hope you have a happy time flying, and we will see you guys next time. Good day.